So, um, so today I want to start to think about what we're going to talk about this week is the shallow water equations. And the shallow water equations are really just a way of rewriting the hydrostatic or maybe hydrostatic Bosonesque equations in a way that's easier to think about. It's sort of quasi 2D. And so today we're focusing mainly on what the hydrostatic Bosonesque equations look like and how to build them and what the conserved invariants are. And then on Wednesday, we're going to start to see how those conserved invariants actually help us link the response of large-scale stuff to this vorticity film that I keep showing. So we're going to see why vorticity is special in terms of the hydrostatic response to, the shallow water equation response to an initial perturbation. Vorticity is special compared to other invariants like energy. And so we're going to start to come to understand that that's going to be the foundation for what quasi-geostrophic and planetary geostrophic equations rely on, which we're going to talk about. We would talk about them next week, but next week is ocean sciences. So we are not meeting next week, but we still have a homework due on Friday, but we start back up on the following week. So this Friday, people need to look at the homework and ask questions, because the following week, you still have to work on the homework, but the last time to ask questions, except for by email, is this Friday, okay? And so everybody's looking at and doing their peer review of last week's. So everybody will have turned in their peer reviews on Thursday. I'll give you back the first homeworks on Friday, and we can have a discussion about any lingering questions on those, but also talking about the next homework set, what the questions are like for that. And the process will repeat again, so the homework will come in on Friday. We'll do a peer review till the Thursday, and then we'll talk about it after, and then we'll loop again. Does that make sense to everybody? So it's typically 2 weeks plus maybe extra time if there's spring break or something in between the homeworks, and so that makes it 6 homeworks, 5 of which are peer reviewed. The last one isn't peer reviewed because it's like just the last day that we're meeting. So the fact that we're not meeting next week means that we're going to go into reading period, and so we're going to have, I think, 5 makeup classes during the reading period, but we're not going to have a final exam. We're going to have a final project, so that's the plan. So we'll just keep continuing on, and if people would like to front load it and like double up so that we have twice as long classes for fewer days in the front of reading period or something like that, we can discuss that when we get close. But we do need to make some makeup time of the few classes that we're going to miss. Does that make sense to everybody? Okay, so starting to head towards vorticity and why vorticity is important, we're going to talk about the shallow water equations. So how many of you have seen the shallow water equations in like a fluid dynamics class or something else? Some of you. Okay, good. We're going to go through it step by step, but we're not going to, because we're talking about 3-dimensional turbulence, this is sort of just a step on the road to understanding quasi-geostrophy and planetary geostrophy. So we're going to go a little faster on the shallow water equations than I would go in like the oceanography class, where we're going to talk about large-scale stuff where the shallow water equations are more valuable. So you'll see there's more detail in Valis than we're going to cover on the shallow water equations. Okay? All right. So we're going to talk about the shallow water, how we get the shallow water equations, and then we're going to talk about the reduced gravity equations, which is useful for thinking about internal waves, and we'll see what that is. And then we're going to talk about some of the conservation properties of the shallow water equations. That's probably where we're going to start, although we might look at some videos of the waves that are coming towards what we're going to talk about on Wednesday. Geostrophic adjustment is one of the most important things that we're going to talk about in terms of understanding how quasi-geostrophy works in the whole semester. So that's what we're going to talk about on Wednesday, but we're going to keep coming back to it conceptually to think about what it's telling us about. And I have lots of videos and other things to try and make that easier to understand. Okay. All right, so here are our equations on a tangent plane. What are some of the things that are in these equations? What have we discussed about these? Where do they come from? Are these hydrostatic or non-hydrostatic or both? Both, because we could either take the vertical momentum equation or the hydrostatic balance. Those are interchangeable. So it's one equation, and it doesn't introduce any new variables to swap between the two. What about the F? Where does that come from? It's the Coriolis parameter and the tangent plane approximation. So on a sphere, we would need a more complicated Coriolis parameter that has like curvature terms and things. Remember, we've simplified down to this local Cartesian coordinate system, and that's because we're thinking about motions that are small, relatively small compared to the whole Earth. So we're going to restrict ourselves to things that are kind of hundreds to thousands of or meters to thousands of kilometers. We won't go to tens of thousands of kilometers with these equations. You would need the full spherical coordinates to do that. But that's not a terribly strong constraint because all of the phenomena that occur on those larger scales also occur in these equations. So from just what's in the equations, this is enough. They're just not quantitatively accurate, even though they qualitatively have the same stuff in them. Okay? Okay, so we want to go to the shallow water equations, and we're first going to start with the simplest shallow water equation, which is one constant density layer. Okay, and so we're going to assume that this layer is thin and wide. So our aspect ratio is going to be shallow. So H is going to be much, much smaller than L, which means that we're going to be able to use what? Hydrostatic balance, which is what we talked about from the scaling. So we're going to assume that it's a constant density layer with hydrostatic balance. So what does that tell me about the pressure field there? dP dC equals minus rho G. That's the hydrostatic balance. So if H is much, much less than L, then this. Now what? Well, it's constant density. So what can I do with that equation? I can just integrate now, right? Because this is a constant. I don't know what the density is necessarily, but somebody would give it to me before I started doing it. So I could say that P at the top minus P at whatever Z level is equal to the integral from Z to the top of minus rho naught G dZ. So where's the top here? What's a convenient place to... So we've got this surface elevation that's going up and down. There's maybe a bumpy bottom. There's an average thickness, big H. There's a local thickness, little h. What would be a convenient place to decide where might I know what the pressure is? Up here, it would be the atmospheric pressure, and if I make my life boring and say that the atmospheric pressure is constant, which it actually isn't, but if I did do that, then I could just set it to be some constant all along the surface. All right, let me explain this a little bit more because this is actually an important point that I think Vallis does poorly. If the atmosphere was hydrostatic, it's very light. So there's not a big pressure difference between, say, the peak and the trough of this. So it is fair to say that the atmosphere is constant in space in terms of the amount of pressure. But actually, in the real world, the pressure deviations between sea surface highs and sea surface lows is about 100 millibars, roughly. which is also atmospheric, like storm to clear skies kind of level. So in time, the atmospheric pressure varies about as much as the sea surface varies, but in space, the atmosphere doesn't vary as much on the kind of scales we're thinking about. So some of the phenomena that come along with that are things like storm surge, where when you have a low in the atmosphere, the ocean actually pops up because it's expanding into the low pressure, and that is directly because of that. But for our simple perspective of the shallow water equations, the boring shallow water equations, we're just going to take the atmospheric pressure to be constant in space and time, and for even more, we're going to take it to be zero. Because if it's a constant, it doesn't matter. Let's just set it to zero. Okay. All right. So what does that leave us with then? What's that integral? Oh, pressure evaluated as Z. Should have said. So looking at that integral, if I go from the top, which we now said is at eta, down to some level Z, what's this integral? This is a constant. So rho naught G, the top minus Z. So, sorry, I just flipped a minus sign, putting this one there. So Z minus eta. Everybody see how I did that? This is just, what's the Z at the top? It's eta. What's the Z at whatever Z is? Z. Yeah, there was a minus sign here and I covered it.
Yeah, but there is something.
Top minus, oh, you're right. Haha. Good. Oh, and that's with Z being negative the farther down you go. I was trying to figure out how I got a positive out of it. Z starts at 0 and goes negative. So the pressure is accumulating with depth. Good, all right, we're good. What does eta depend on? Is it a function of Z? But it's a function of X and Y in time. So I want to be explicit about this. Okay. So let's go back to our equations of motion. So we used this equation, and that's how we got this. We just solve for pressure now. So this is the equivalent of the hydrostatic balance. We don't need the hydrostatic balance beyond this solution. What do we do with that pressure now that we found it? We need to do what in the first two equations? Exactly. So what's the x derivative of this? Does it depend on Z? No, because this is pure bare Z, and it's a partial derivative with respect to x, so it does not sense that. And what about the next one, the y one? This doesn't depend on y either. So it's a pure derivative. So 1 over rho, and we can put rho naught dp dx is what? That's it. Okay. So, and same thing for the y one. So now rho has disappeared from our equations. We don't have it anywhere anymore. Except for in the mass continuity equation, which we're going to get to. But, and we don't have P anymore either. We just have eta. So, from this, with that solution, that's what our equation of motion looks like now for the horizontal. And we actually don't even need to write the hydrostatic equation anymore because it's already done its job in giving us this. So now we just have two horizontal equations of motion. We no longer have a vertical equation of motion. It gave us this, and then we're done. Does that make sense? Okay, so what about continuity? Let's go back to the big picture. How about continuity of mass? If the density is constant, what does continuity of mass look like? Looks like non-divergence. So our normal one or the other one both cases these go 0, 0, but if rho goes to rho naught, then this is 0, this is some constant, so it just becomes this. Is that a 3D or a 2D divergence? Careful. Is it a 3D or 2D? We are in hydrostatic balance. Is that a 3D or a 2D divergence? We have subsumed this equation of motion to have no W in it, but there's still a W in this equation. In fact, that's how you determine what the W is under hydrostatic conditions. So this is du dx plus dv dy plus dw dz equals 0. Okay?
If this was two-dimensional divergence, then it wouldn't be rho, it would be h or something. It has to be
Right, we're trying to get to an h equation, but even in the h case, there is some vertical velocity. It's just highly constrained. So let's think about where it comes from for this picture. So if I'm moving this way and stretching like this, what does that represent in my horizontal velocities? If I go, suppose I go over a bump in the hole without changing the surface height, what happened? Gotten taller. So it had to converge in order to get taller because I can't change the density, right? The density is the same. Likewise, if this surface is going up and down, suppose a wave, it's converging and diverging underneath in order to account for that. There is a little bit of vertical motion because when you converge and diverge in the horizontal, you've got this part. That's exactly, it's the W that allows you to fit into the hole. But the W is totally passive. All it's doing is setting the thickness as you go over bumps. So if we knew the thickness, we could infer the W from the thickness. Does that make sense? So how do we get an equation then for thickness from all this stuff? So we have this. We think this is the governing equation. How do I get to a thickness equation from that? What kind of equation is this?
flux equation. Coming in and going out. So if you take a control volume with h into u, that h into u integration coming in is equal to 0. And from there we get it.
So that's exactly how ballast does it, which is this. So here's the flux of d by t of h is the convergence of h into a spot. So if it converges, this goes up. If this diverges, it goes down. If it converges, it goes up. That's the whole game. And we know, because we've played this game a bunch of times now, we can distribute this derivative and write it in that form as well. Right? That's just distributing out the derivatives. We could also have done it more formally by integrating this in the vertical. So thinking about things like this where rho u times the surface containing, and then you integrate in the vertical and you gain h's when you integrate in the vertical. So if I integrate each term in that equation in the vertical, I'm going to put the u and v together. U plus dv But if the surface goes up and down, oops, sorry. What's this? This is a perfect derivative in z, integrated in z. So it's just minus w evaluated at eta minus w evaluated at z. So if the bottom was flat, and we went all the way to the bottom, this would be 0. What's w of eta? It's not 0. It's if this surface is going up and down, that's the w. The velocity is tracking the thickness going up and down. So w of eta is just d eta dt. If I use the same logic for the bottom, I could write this minus d eta bottom by dt. Sorry, the minus sign. Or dh dt. The top minus the bottom. Oops, I lost track of these symbols. The top one minus the bottom. So the WdZ integrated from the top to the bottom is just the rate of change of the top of the bottom going up and down. And then this side is a vertical integral of the horizontal divergence, which is this equation. Okay, so everybody's on board. We can do it either way. We can do it formally, mathematically, by integrating in the vertical this equation, making sure we set the surface and bottom boundary conditions right. And that gives us the dH dt that comes from the dW dz term, and this comes from the ddx of u and ddy of v. Or we could do it the way that Akash did and just intuit that this was a converging thickness flux into a spot, and write down this equation from intuition. They're the same thing. This is Akash's version is the physical way. This is more the mathematical way. Okay, so here are the equations then. How many unknowns do we have? Which are? Yes. So in this process, W has now become passive, the same way that pressure became passive once we had used the hydrostatic equation. So we've used the continuity equation to eliminate W. So we just have a thickness equation. We have a V equation. We have a U and V equation, and a thickness equation, which can be written either this way or this way. So we have H, U, and V, and eta. They're not quite the same, but they're almost the same. Let's go back and look at the figure again. How is H different from eta? Constant in space or constant in time?
So it's constant in time, it isn't constant in space. It's like the surface of the ground.
Yeah, so this eta B, eta surface minus eta bottom is H. Eta surface is varying in time and space. Eta bottom is only varying in space, but it's at least given to us in advance. So it is slightly more complicated than those four equations. We also need an equation that tells us about what's happening in the surface and the bottom, but it's easy enough to write down, which is eta top minus eta bottom equals H. This is given, this is solved for using those equations. Does that make sense? Okay. All right, so it's a closed set with four equations once we throw this one in. What happened to the temperature equation? Exactly. So the temperature density relation, the temperature equation is still there if we wanted it. We could still diagnose U and V and W from this and predict how the temperature moves around, but the temperature doesn't affect the density because we took the density to be constant. So it's an uncoupled equation, even though it's still there. The same would be true of salinity, the same would be true of fresh water. You can keep track of those things in the shallow water equations, but because of the constant density case, it doesn't come back to drive our system. So is this a decent approximation of the real of a real ocean or atmosphere? What do you think?
Not for the atmosphere,
Why not?
because the density varies.
So what kind of motions come from the density variation? We've already talked about it.
Like convection.
Convection is a good one. So this definitely does not cover convection. Okay, what else? Baroclinicity, or the thermal wind flow. So remember last time we talked about the thermal wind and the shear and that being part of it. So in this system, we definitely don't have convection. We don't have vertical motions driven by hot or cold air or water, or salty water or moist air, for that matter. But we also don't, which would be non-hydrostatic motions in the first place. So even the hydrostatic equations have a hard time expressing convection. But in addition, we don't have thermal wind because we need a horizontal density gradients to get the vertical shear in the geostrophic balance. So there's no vertical shear in these equations. It went by fast when we wrote down the pressure part, but let's go back. If the pressure doesn't vary in Z in an interesting way, the horizontal pressure gradients in X and Y, then neither does the velocity. So these velocities are not sheared. Even with this part, they're not sheared. It's a little bit funny. There's a weird exception. You could put some shear in the initial conditions and it would continue to evolve in this system, but it wouldn't be driven by any pressure gradients. So it's hard to imagine how you would start it other than just saying it was there and then letting it evolve. Does that make sense to everybody a little? That's kind of a weird exception, which is not true of the geostrophic equations, which are explicitly forbidden. There would be no vertical shear. There could be some in the initial conditions here that would kind of slosh around for a while. Okay? All right. So, that's the shallow water equations. Here they are. So we're going to talk about some things that are in there. But what if we wanted to put just a little bit, just a touch of interesting thermal wind stuff into these equations? There's a nice way to do it called the reduced gravity equations, which instead of a layer of constant density sitting on top of a solid bottom, what if we have a layer of constant density sitting on top of another layer, higher density, but we insist that this one doesn't move? How is it different from this case?
In the smallest change, the smallest time change.
Yeah.
The bottom vary with the time.
The bottom could vary with time, and the bottom will vary with the flow above in a weird way. What we want to do is we want to eliminate motion down here, which means we want to eliminate all the pressure gradients down here, so there's nothing to drive any motion, but that's a constraint on the surface. Does that make sense to everybody? Whereas this one, this doesn't vary in time and it's fixed in space. So it's a little bit different. But from the hydrostatic relation, We had a pressure equals 0 at the top, and then it goes up to Z at the bottom. How is this going to be different in the hydrostatic balance? Okay, so if I'm thinking at a particular Z, which happens to be the one that's the location of the bottom of this interface, I can do that. I can still use the same pressure integral. My surface boundary condition is the same. But what does it mean to say the bottom layer is motionless? I said it before quickly. I want the pressure in the next layer down to be what? Constant, at least in space. So is this enough to express constant? So if I take, a particular slice, that's telling me the pressure, but it's telling me the pressure on a curvy surface. What's the pressure down here? I need to draw this out of phase, and I'm not being able to do it. There we go. If I have high pressure here because the surface height is high, at theta top, what does this surface need to do to make it have no high pressure here? It has to push it down. Why is that? So another way of thinking about the hydrostatic balance, which is a nice way to think about it, is the pressure is the weight per unit area of everything above you. So this is the mass per unit volume, and then I've integrated in Z, so it's now the weight per unit area. So what's the weight per unit area of here? It's just that height, the anomaly, plus however much there is on the average. When I get down here, I have this amount of stuff of low density fluid, and then this amount of stuff of high density fluid. Or here, I have this amount of stuff of low density fluid and this amount of stuff of high density fluid. So if everywhere that this goes up, this goes down, once I'm down here, I have a higher surface, but I have more light. Whereas here, I have a lower surface, but I have more heavy stuff. So, in the pillows and bricks stacks, which is key to thinking about this, if I have a stack of pillows that starts higher up than its neighbors, I might end up with the same weight down here because I have fewer bricks but more pillows. Whereas here, I have fewer pillows but more bricks. So I could still end up at the same place. So everybody understand what I'm saying for the weight? So what this means is in the reduced gravity system, in order to have no horizontal pressure gradients, the depression downward of the upper layer is linked to the surface elevations upward. They're not independent of each other. They are, in fact, proportional to each other. So, where's the math? Here's the math showing that going through. But what it means is that you can either think of, if this one's proportional to this one, I can write du dt plus f cross u equals minus g eta top, or plus g, dx, gradient. Horizontal gradient. Eta bottom. So there's a flip of sign, because when the top goes up, the bottom goes down. Everybody on board with that? But I can write it either way and I get the same answer, because they're not independent of each other in the reduced gravity system. Yeah?
So we're no longer assuming that the density is constant.
The density is constant within the upper layer, but it's different in the next layer. So the density is constant in this whole layer, and in this whole layer, but they're not the same densities. So this is like a warm layer sitting on top of a colder layer, but the density is still constant within the warm layer.
So does the two layers on the top be parallel to each other to hold a constant weight? of the second?
Exactly. In order for there to be a constant weight above, when you get below, the two interfaces, the surface and the layer 1, layer 2 interface have to vary together. And there's one other piece which I didn't. This is actually a different value of g when we write it for the bottom one. G prime, which is g times rho 2 minus rho 1 over rho 2. So is this, which one is bigger, g or g prime? G, because this thing is going to be a fraction of the rho. So if, say, the next layer down is 100th more dense than the top one, this is 0.01. Everybody on board with that? So the reduced gravity system, okay, now here's another question. Well, how about my H equation? H equals eta top minus eta bottom. Which one, if these two pressures are equal, which is a bigger jump in height, at the top or at the bottom? This equals this. G prime is smaller than G. Which is bigger? The bottom one. The bottom one has to go farther to get to the same pressure because it has a smaller coefficient out front. So this is approximately equal to just minus A to B. So our H equation in the reduced gravity case is actually almost totally determined by the motion of the lower interface, not the upper interface. For the thickness equation. For the pressure equation, it could be either the top or the bottom. They're both linked together. They both tell you the same pressure. But if we want to have a closed system, we can think of this as being for the bottom interface. This is the bottom interface. And then we have a closed set of equations. Does that make sense to everybody? So the reduced gravity is a little bit funny, but it allows us to do some things really fast. Because, so we could have a wave that was propagating in the surface and also propagating on that interface below. And the reduced gravity system would allow us to calculate that kind of wave, which is different from a wave that's just propagating at the surface and going all the way to the bottom. And we're going to see that that's a key difference in how fast those waves go, what we call them, how we think about them. And we'll talk about those in a little bit. Okay, so we have the reduced gravity shallow water equations, and we have the full shallow water equations. So the full shallow equations go to the surface to the bottom, then they have constant density. reduced gravity, we might have an interface between light water and dense water, but we assume the dense water doesn't move. It's just the light water that has all the action. That's enough to get a good handle on the rough kinds of motion that are in the ocean and atmosphere that we want to talk about for quasi-geostrophy and planetary geostrophy. Okay? All right. So let's take a look at some solutions. Sorry, that's just doing the same thing. Okay, here's one. This is the hydrostatic pressure of gyres. So, what's the pressure like in the surface layer?
Just depends on Z.
It depends on Z, but wait, the surface is lifted. So in the middle of the gyre, there's more pillows. So is it a high pressure in the middle or a low pressure in the middle? High pressure.
Same.
But then below, there's actually a canceling effect because the picnic line goes down. And so there's almost no pressure gradients below. So a gyre, a subtropical gyre, is a high pressure anomaly in the center, and it has geostrophic motion around. And if you want to, I added these equations so you can stare at them if you want. Vallis doesn't even write them in the Essentials book. But you could do a 2-layer, a 3-layer, a 5-layer, a 20-layer. You actually can build up the shallow water equations and stack them. And in the limit of an infinite number of layers, you are back to a discrete version of the full hydrostatic 3D system. This is really a numerical method in the limit of very many layers. Okay? So it's kind of, we're playing games with the 1 layer and the special reduced gravity version of the 1 layer, but really what we've done is we've started down a numerical discretization of the continuum equation of motion. And it's convenient because we can analyze 1 layer versions, we can solve things, but actually many real ocean climate models are multiple layer using stacked shallow water layers. Okay.
In the second layer, there is no geostrophy, there is no balance.
There is, and it's 0 on both sides of the equation. So, yes. It is geostrophically balanced. The raw speed number is small. In fact, it's 0. And the geostrophic velocity is also 0. And the pressure gradients are 0. So, yes, it is geostrophic across the board. But in the reduced gravity system, in this system, you have to think, all right, so the position involves all of the thicknesses together, and the pressures actually, it's a generalization of pressure called the Montgomery potential, and involves they're complicated linear coupled equations through all of the pressure terms. So, the H3 equation appears in the first layer pressure, which is super complicated. So it's really tangled. So you can do lots of funny things with these and solve them, but it's a lot more algebra than we want to deal with for this class. Does that make sense to everybody? Okay, so what's conserved in shallow water equations? So, what about energy? How would we get energy out of those equations? Here's one. I'm just going to write this H there. Sorry, so this is the flat bottom case, which will make our life a little simpler for the moment. What do you think is conserved in this system? How did I make energy like in the homework problem? Kinetic energy. So before I multiplied by U and then went through, I could do that again here. Would that be the energy or not? And here's the exception to think about. What if there's a really tall wave next to a really short spot? If I just do U dot U, What does that tell me about the energy of those two locations? That would be the energy per unit height. So we might want to actually dot by U and then integrate in the vertical, so that we would have the energy density just in X and Y. But if it was thicker, it would have more energy. If it was thinner, it would have less energy, just because there's less mass there. So we might want to be careful about that. So that's what this equation is. This is HU squared over 2, so that's just U dot and pull the U inside. And then there's also a vertical integral. And it's, here it looks more obvious there. And then this is what you get on the other side. How do you get this one? From this. Right, so we dotted it with the U, and then we integrated, so we got another H, and then you pull the H inside, because an H inside and an H outside. So gradient of H squared is giving you the H. That's going to be the one that comes from the integral. Does that make sense to everybody? So HU squared is the kinetic energy integrated. And this is like a flux, an advection. And then this is like a flux, and this is like the conversion between kinetic and potential energy. Here's what the potential energy looks like, rho naught GZ, which looks an awful lot like the potential energy just of like a mass, G times Z, with rho naught being its, but since rho naught's a constant, it's not so complicated. You integrate this one in Z and you get rho naught GH squared. So that's what the density is, and you play some algebra between this guy and this guy. So this is the governing equation for that quantity. You add these two together, and this is what your energy equation looks like. HU squared plus GH squared, 1/2, that's your kinetic plus potential. And then here's the flux, which has that same energy plus an extra one. What's the extra one? Remember back to our other energy equations? We had an extra one that was like a pressure work term. So in this case, it's extremely confusing because it looks exactly like the potential energy term. It just doubles it. But you get a non-advective flux. You actually have work. You can do pressure work, which looks awfully lot like the advection of potential energy. Okay? So energy is conserved. Interesting. And if you integrate all the way out to the boundaries, U is 0 at the boundaries, so the energy is conserved. So energy is conserved over the whole domain, and you can do a local conservation of energy equation like we did before. And we're going to have to pick this up next time, but there's also a vorticity that's conserved. There's regular vorticity and potential vorticity that are conserved. And so this is going to be the key to understanding geostrophic adjustment, is what happens to the potential vorticity and the energy as the flow evolves. Okay? So that's where we're at.